Word up. Nationwide hated. Nickel plate.
SQL or death? Yo, son, what are you going to choose? Yo, check it. This seminar is filmed at Carnegie Mellon University. Thanks a lot, Google.
All right, guys, it's the last talk of the semester. We are super excited today to have Michael J. Sullivan, or Dr. Sully, as he is known, give a talk today about the query language that they've been building to replace SQL at GEL, formerly EdgeDB with EdgeQL. So Dr. Sully got his PhD here at Carnegie Mellon's Computer Science Department in 2017, and he is considered distinguished alumni. So we appreciate him taking the time out of his day to come talk to us about what they're doing at GEL. Sully, the floor is yours. Thanks for being here again.
All right, thank you. All right, so I'm going to be talking about the talk's titled Replacing SQL and Improving on the Relational Database Model. We've got replacing with asterisk though, right? So the title of this seminar is SQL or death, but we've wound up ending up a little bit at, SQL and death, right? All right, so I'm going to talk about what we're doing and why. I'm going to give a brief tour of EdgeQL, because even though we've renamed the company from EdgeDB to GEL, we've kept the query language the same name. I'll talk a bit about how EdgeQL is implemented, and then I'll talk a little bit about what we've been doing to still support SQL and why. All right, so you've probably seen a bunch of slides like this where people talk about why they're trying to do something other than SQL in the seminar, but I'll give mine, which is SQL's half a century old. It's showing its age. The original sort of design target was writing ad hoc analytic queries for businessmen. But some of its problems are it's not particularly orthogonal. It's hard to build up queries from subqueries. You often need to restructure things substantially because of things like the distinction between scalar and table expressions. It's broadly speaking a pretty large language that's evolved over a long time and tends to be fairly inconsistent in the ways things are expressed. It has this notion of null that can go in any type and behaves in weird ways. And of course, like I said, it was originally designed for sort of ad hoc business analytic queries, which is something of a mismatch for a lot of application code, right? You have this object relational impedance mismatch where in SQL, you have rows of data, but in an application, you probably have objects linked together with pointers. But despite that, sort of like I think Tony Hoare famously said about Algol 60, it still manages to be an improvement over most of its successors, which we feel tend to throw the baby out with the bathwater. The baby here is the relational model. And I'm being a little unfair here. Obviously, their engineering is the study of trade-offs. And so it's not like they're throwing this out for nothing. But so what are some of the things we think are common problems with these databases that have moved on from the relational model, these NoSQL databases? Well, often they have sort of no declared schemas or weak schemas, or a bunch of this talk was originally written for the PL group. So Bob Harper would call these unityped databases, as there's sort of only one type. They typically have no or much more limited than SQL query languages. Often you need multiple queries to fetch the data you want. This is the N+1 problem, where if you want to, say, fetch a user and all of their posts, you issue that one query for the user, and then you need to issue N queries to fetch their posts. This is also a huge and very common problem with object relational mappers for SQL itself. So often, if you're using SQL, you're not actually avoiding that problem. And then also, it typically comes with weaker consistency guarantees than SQL databases usually have, relational databases. And of course, some of these come with corresponding advantages. These are engineering trade-offs. We just sort of don't usually like the side they're on. I got a Drake meme, but I think we're sort of past Drake memes as a society, but I couldn't come up with a good like Kendrick Lamar meme to replace it. So we've still got those. All right, so what is GEL? GEL, formerly EdgeDB, is a new database. It is what we call graph-relational, which I'll dive into in a minute. But importantly, it is powered by Postgres. It is built on sort of the solid relational core and uses that as its backend and data store. All right, so what do I mean by graph-relational? So we think of graph-relational as an evolution of the relational database model. It is built around having strongly typed objects that have unique identity. These objects can be connected with links, and they contain set valued attributes with specified cardinalities. And I'm going to go talk about this all in detail. But I should also say our marketing has moved away from this. We used to talk a lot about how object relational, and I've got a jacket back there that says object relational FTW on the back. But mostly we've sort of stopped talking about it. We found as a marketing thing, it wasn't really resonating with potential users. But this isn't a marketing talk, and I still like this framing, and I think it sort of explains well what we're doing and how we're doing it.
I mean, is a side comment, like, is it because people are thinking, oh, it's your graph database?
Yeah, also it's a bad name.
Yeah. Okay.
It's a bad name. Honestly, I think that a better name for the model would have been object relational in terms of precision, but in terms of naming, that would have been a full disaster. We thought of type relational, but wound up settling with graph relational, which I wasn't totally sold on. But I think the sort of ideas that we packaged in graph relational really are the core of what we're doing. But the name is probably misleading, which has been obviously, and I'll talk about this more later, naming, or maybe if there's time, naming has been a struggle with EdgeDB, now Gel. All right, so a quick terminology mapping, sort of about, broadly speaking, how relational concepts map into our model. The relational notion of table or relation gets turned into graph relational object type. Columns or attributes get turned into either properties or links, depending on what they're pointing to, and we'll talk about that more. And rows or tuples usually get turned into objects. All right. So diving into those sort of 3 points of graph relational, all objects have a unique identity, which is implemented with a globally unique identifier. So this is sort of a primary key for every object, and it's global and automatic. There's nothing super interesting about this, but it's sort of the foundation of a bunch of other things, particularly our notion of links. So objects can be connected by links. So here you can see a snippet of Gel's SDL, our schema description language, where we've declared a type person that so far just has a name, and movies, which has a name, a release year, and then a multi-link of actors. So that means each movie can contain or reference 0 or more person objects. These links can have properties of their own, which we call link properties. So for this actor schema, every actor link could have a character name. As a matter of syntax, we also allow omitting link and property, which is a little bit an example of us moving away from this graph relational marketing where we think, where we talk about links as being they're very special, but they sort of still are, right? They're the things that reference other objects and they can have properties. I also talked about attribute cardinality and how objects contain a number of attributes that have different cardinalities. And so the sort of 2 axes here is every property or link can be either optional or it can be required, and it can be single or it can be multi. So here we have an example movie type that has an optional description, required but still single title, a multi but optional alternate titles, and then a required, so there must be at least one, multi-list of actors, which is actually bad schema modeling. There are movies that have no actors in them. But this is a departure from the sort of exact terminology mapping I was talking about, because in the relational model, right, you have tables and they have attributes, and they can be nullable or not nullable, but they always are one thing. Whereas here we've got these multi-properties that might have multiple entries in them. And we'll touch back on some of what that allows us to do later. All right. So now, having talked a bit about our schema model, it's time to dive in and see how we query it and what we do with it. So I'm going to be running through some queries. Here we've got query text up in the cyan block, and then in the gray block we've got the result of the query, approximately as formatted by our command line interface print loop. All right, so here we're selecting a string literal, and we get back a set containing that string literal. And the set's sort of important here because in EdgeQL, sort of everything is set valued. That's not too interesting, and neither is this, but because everything is set valued, any expression can return multiple values. And so the question is, how do you operate on something using multiple values? And the answer is we typically, the core semantics for most operations is to lift them over the Cartesian product of the inputs. So here, if we're trying to add together a set containing 10 and 20 and a set containing 1 and 2, we get 11, 12, 21, and 22. We've got with bindings, expressions can be bound to variables. So here it's the same thing, but one of them is named. And then additionally, we don't have any notion of null. What we have is just a continuation of our set valued semantics. So if you want to treat something that isn't there, it's an empty set. And so here we have the empty set being added to some non-empty set, and we get an empty set back because these operations, like mentioned before, will take the Cartesian product, and the Cartesian product of an empty set with anything is another empty set. This has like a really strong mathematical background in our formalism, but is also sort of borderline, like especially when you get into filter things with ORs, because true or the empty set is the empty set. And there's like good reasons we do it that way, but also not all of our users like it. So
sorry, you said borderline? Like, what do you mean? Like it's kind of like sketchy? Or what are you trying to say?
I'm saying that there's potential for user confusion, and we see it on occasion. I think semantically, like there's a good reason why we do what we do, and it's easy to explain what the rule is, but it's still not that hard to get tripped up by it.
All right, thanks.
And we've been thinking about what we can do to mitigate it, but don't have a clear answer we've decided on yet. So function parameters then some functions have optional parameters that allow them to cope with and have behavior other than producing an empty set when one of their parameters is optional. The core one being the coalescing operator, which if given an empty set as its left-hand side, produces its right-hand side as output. We also have coalescing equality. So you can compare something that's potentially empty to something else and get back a true or false, even if something's empty. We also have aggregating functions such as count and sum and array ag. And so here you can count that set addition from before, and you get back that you have 4 things. But you might be asking, okay, the whole point of a database is to query data. So what are we doing? Just like messing around with empty sets of integers? And you're right. So let's do some queries with actual data. We're going to be querying that sort of movie database that we mentioned earlier with movies and actors. So the basic query here is select movie, and we get back our movies. And what actually gets returned is the movies just with their unique IDs, if you just ask for that. But we probably want to see some actual data. So we allow adding a shape to object where you specify shape to objects, where you specify which properties and links out of the objects you want. So here we're asking for titles and release years, and we're getting those back in our data. You can also filter in select to try to, obviously reduce to get the data you care about and not all of it. So here we've added a filter, and we're only looking for movies called Dune, and we write that with filter movie.title equals Dune, or the shortened filter .title equals Dune, since we're in a select and we know what we're referring to. Now, I've said that this is an extension of the relational model, and of course the heart of the relational model is a join. So you might be asking, okay, give me give me something with a join. Let's see what that looks like. And they'll give you something that's sort of like a join. Here, we want to get all of the movies named Dune, what year they came out, and all the actors in them and their actors' names. So we write that with a shape, and in that shape, we put our link actors, and then we can put a sub-shape on that saying what we want to get out of that is name. And so here you can see we're getting our 1984 and 2021 Dune movies. The latest one doesn't come out because that's Dune Part 2, so it doesn't match this filter. Now, from like a SQL perspective, this joins three tables together. If you wanted to write something like this in SQL, you'd be selecting from the movie table, from a person table, and then also from a link table that's like movie actors that says what actors are in each movie. But unlike the sort of naive way of doing that join, we actually return the nested results nested instead of flattened. So the values we return, you can see we're returning movie objects, and then inside those movie objects, we have a list of actors. Whereas the sort of traditional way of doing this in SQL, you would get back like movie names paired with each of the actors in the same rows. Now, if you remember, we also had a character name link property on these actors. And so if we want to grab that as part of our link, we can too. And so now we're getting all the actors along with their character names.
I'm so sure you can explain this in a second or not. So this is a one EdgeQL query, goes over, hits your server. You guys compile that into SQL.
Yeah.
Is it going to be, so using the previous example without the link, like, are you going to convert it into that join or do three separate queries?
We're gonna generate one query, and we're gonna return those results basically directly to the user.
And then are you going to let the database server construct the JSON response, or does your middleware do that?
So we have there are for the actual response, I'll touch on that. I'll touch on that in a later slide.
Okay, sure.
I've got a slide about what our output formats are.
All right, thanks.
Yeah. All right. So we're grabbing these character names, and then just to show you a bit more advanced of a EdgeQL query, here's the sort of actual query against that test database I ran to produce those results. I grabbed actors. I filtered for things that matched any of where the character name was like, using the SQL like operator, any of Chani, Paul, Duke, or Gurney. And then I ordered that by character names. All right, so it's nice to be able to fetch data from databases, but you also want to be able to do some processing or collect derived data. So we support adding computed fields to an object. So here we're selecting titles and we're computing the size of their cast by counting the actors link. This is probably not good data quality. I think none of those numbers are like right in any sort of real sense. And you can then, once you've declared a computed field, you can use it in further computation. So here we're computing cast size, and we can filter for movies that have a cast size greater than 50. The sort of mental model you should have of what these computed properties do is that the shape we evaluate for each object, and then any computed fields are attached to the object and can be grabbed later. All right, so what are some other queries we might want to do? Let's say we want to, for an actor, find all the movies they're in. So you could write that like this, where we select a person, we filter on their name down at the bottom for the actor we care about, and then we're defining a film's computed link. And the way that's defined here is we're selecting all movies, and then we're filtering the movies for if person, which is bound to this outer person we're selecting, is in movie.actors. And that here you can see does exactly what we want. But this is a really common case. And so we actually have built-in facilities for doing this called backlinks to allow traversing a link backwards. And so if you want to find all of the persons that are linked to by actors, you can say, give me anything that has an actor's link to it that is a movie. And so we can grab those easily. To support efficient backlinks, since that's a core feature, we basically always put indexes on links. So this should hit indexes. Computed properties and links are a really core part of EdgeQL. And so we've also extended them to the schema. So when you declare a type, you can declare built-in computeds for that type. And that sort of thing I just showed you is a really common use case for this. You can have, so for example, if we have a person, we might want to declare that sort of film's length that is all the movies that they are an actor in.
Do you materialize that?
No, we don't materialize that. We compute that
on the fly.
Yeah.
Okay, thanks.
So we've got a couple more sort of schema language features I want to touch on before we dive into the implementation, because some of them will get mentioned there. One of the big ones is we support inheritance. And the place where that shines the best, we find, is when you're trying to do mix-in style things where you've got some pieces of data that are going to show up in a lot of different objects. And so here, an example that you could do for that is, let's say you want a digital object identifier on a bunch of objects, and you also want names. So you can declare an abstract type for digital object with a required exclusive DOI and an abstract type for named, and then different things can extend them and pull those into those objects. And so here we've got a movie that's both those, a named digital object, TV series, which is the same, and episode. And so they're all separate things, but they all sort of pull in some of these behaviors. And just as a schema modeling example, here you can see we've got a TV series object that doesn't have a built-in link to its episodes. Instead, we put required link for each episode that says what series it belongs to. And then the episodes in series we compute with a backlink. Our users love inheritance, but it is a pain in my butt. A lot of our trickiest implementation problems come down to this. And we might touch on some of them depending on time. To just run through a couple other of our schema features before we dive into implementation, we've got access policies, which is you can define pretty sophisticated access rules on objects for when you can select them, when you can insert them, when you can update them, that can reference global variables that you define when setting up your clients. We have triggers, and we have default values and rewrites, which allow you to rewrite fields and objects whenever a update is done. All of these are defined with arbitrary EdgeQL queries, and all of them are implemented in the compiler. We don't build them on top of the most similar Postgres features, because the most similar Postgres features typically aren't powerful enough to express arbitrary EdgeQL queries, because they're usually sort of looking at a row at a time or a table at a time, and we need to be able to look at multiple stuff. So we actually have a formal model of a core calculus of EdgeQL that covers a lot of the behavior we've discussed, and a somewhat more fleshed out executable model implementing it, implemented and designed by Jibo Chen, who is, I think, on this call, and who's a first-year PhD student at CMU now, back when he was an intern with us. All right, but so now it's time to dive into the fun bits, which are the implementation. At least the sort of fun bits. So the sort of core idea of the implementation is we are built on top of PostgreSQL. Every one of our schemas get turned into Postgres schemas, and every one of our queries gets compiled into a Postgres query. And as Andy was getting at, every one of our queries gets compiled into a single Postgres query. So when you have one EdgeQL query, that gets compiled into one SQL query that gets sent to Postgres and executed directly.
And maybe you can touch on a second, it's stock, it's like stock Postgres, so you're not installing any extensions or UDFs to make gel work.
Yeah, that's right.
Okay.
I think the version we run on our cloud has has one patch we ship to make creating constraints faster in one edge case. And I think that's as far as we have it hacked up right now.
Okay, awesome. Thanks.
because one of our users was dying from something stupid. Okay, so to loop back to our terminology mapping, I was saying that broadly speaking, SQL table is a object type, a column is a property or link, and a row is an object. So we're going to flip that around and then see what's changed when we go to actually implement it. So our actual schema mapping is an EdgeQL object type becomes a SQL table. A single property or link becomes a SQL column, but a multi-property or link also becomes a table because it has to link the sort of source and destination. So first, single links and properties. We've got a optional property name, and so that's just a text column. If we've got a required link to some object foo, that's a UUID column referencing that object's ID. We'll put a not null constraint on it. And then we also, for all links, create an index for allowing reverse lookups efficiently. The column names in the actual database are not these real names. They're actually the UUIDs of the objects in our system. And actually, the UUIDs are the like unique identifiers in the graph-relational model, because our schema is stored as a, in EdgeQL, right? That's all bootstrapped. Note also that we have an index, but we don't have a foreign key constraint because that is sort of doesn't work with our multi-table implementation of objects and inheritance, and would not help, like, and would cause, I'm sorry, and would have some performance downsides. Instead of having explicitly specified foreign keys, we ensure in the compiler by construction in our query language that you only try to put in links to objects that actually exist. For multi-links, like I foreshadowed before, we create a table. So if you have some multi-link foo from an object bar, we'll create a table that could be named bar_foo, and it has source and target UUIDs, and then a unique constraint on those, and then a index for looking up it backwards. If we have linked properties, then those go into these link tables. If we have multi-properties, it looks pretty similar, except we only, actually this is right, there shouldn't be a unique source. There's no constraint on this. So ignore the last line of this. It's just a table with source UUID and target text. I was editing and missed something. Maybe we can fix that in post. That's probably more of a pain. All right, so now that we've seen how the schemas are mapping, what does the compilation look like? So we compile EdgeQL into PostgreSQL, and we do it in sort of two phases. We have our query language, which gets compiled to an intermediate representation, and then an intermediate representation, which we compile out to SQL. So it's a pretty like standard compiler architecture. The question is always just like, how many intermediate representations do you have? And so to sort of run through some of the things we do in the compiler front end, we've got name resolution in the front end, which for all the names referenced in the query, figure out which schema objects they reference. So, user is user, deck is deck, name is name, This is interdependent with a type inference pass, which will determine that, user is user, deck is actually a card, names are both strings, and this dot name equals Alice is a Boolean. Type inference also needs to construct new types in a number of cases. So if you are putting computed properties on your types, that actually extends the type. So here, if you have num gets count of deck, the type of this returned object is user, but extended with a single property named num with type in64. And then the question is, how do we know that's a single property? And well, we also have a notion of cardinality inference, which is one of sort of our core ideas. And so here, as we analyze this query, we discover that user is many, which means it can be at 0 or more, any number. And that's the cardinality of any table in the database because you can't know how many rows it's going to have. Dec is also many because it is multi, but not required. We compute that name is 1 because it's a required property, and also that this count is 1 because count aggregates Dec and produces one thing. And then we also can compute that this entire expression has cardinality at most 1. And we can do that because name is an exclusive property. And so at most one object can have that name. And so this is also how that type inference on the previous slide was driven. Since we can compute that num has cardinality 1, then we know that it's a single num. There's also another cardinality mentioned here, not mentioned in this slide, at least 1, which corresponds to something being required and multi. Then there's also this notion of shape inference, which drives into the information we return to our clients, where we figure out which fields are actually being returned from the object, and we produce something that gets sent. In the front end, there are also a bunch of other desugarings. If you are casting an int array to an array of strings, we turn that in the front end part of the compiler into an unpack of the array, a cast, and an aggregate. A number of things like that, along with resolving overloaded functions, inlining definitions of computed properties and links, because like we mentioned before, they're not materialized. Sometimes inserting implicit limits and type name computations in, because the CLI likes to say, don't give me a set bigger than 100 and make sure every object tells me what the type name is, where we do most error checking and do some fiddly things like ADA expanding array and tuple expressions for annoying technical reasons. All right, so that's all the front end.
What would be an example of an error that you can't check at that IR conversion? So the previous slide says most. You say most error checking. So what are you missing?
Any of the error checking done later, I think, is usually for annoying implementation reasons and probably should be done earlier. Like I know there are errors we generate out of the SQL side, and I can't remember off the top of my head what the static ones are.
Okay. Awesome.
We've been trying to get rid of them.
They're like safety nets, just in case.
Yeah. We're supposed to generate all the errors in that first phase, all the static ones, but I'm pretty sure we don't.
Okay, thanks.
And then we also have dynamic errors that get generated, by Postgres, because there's some Postgres error. And then we have a phase in our server and compiler infrastructure that will try to interpret those and remap them into something that explains what's going on from an EdgeQL perspective. And that's both sort of built-in errors and then also ones that we explicitly trigger in some cases. The backend architecture of the compiler from the IR to SQL generates SQL based on the IR and then also based on something called the scope tree, which is a way of implementing a bunch of language features that we're in the process of ripping out because they were complicated and didn't make sense. So the last time I gave this talk, I talked about those a bunch, but since then we've decided to remove them and are sort of halfway through a migration process. And Jibo did a lot of the work in sort of helping me make the case that these don't make sense and we should pull them out. But so we build the query, I would say semi-lazily during this part of the compiler. So as you traverse the IR tree, you'll see, we're selecting from this object, this type. And so we'll generate a SQL query that selects from that object, but we won't fill in anything into the select clause, any column accesses. And then later, once we try to apply a shape to that object, we will dive back into that original SQL relation and go insert the column accesses and patch up the query to be actually fetching the data we want. And this architecture was probably a mistake. It's pretty complex, and we should probably have another step of intermediate representation where we figure out what we're trying to get before we try to start building SQL with it. In the IR to SQL compiler, we also generate SQL that serializes the result into the appropriate format, and I'll talk a bit about that on the next slide. And then handles various specialized handling, especially for mutations, where our mutation language is pretty complicated or is pretty powerful, and sometimes requires special enforcement for things that SQL doesn't understand. For example, we allow properties and links to be required multi, which means there needs to be at least one. And there's sort of nothing that corresponds to that in SQL. And so we need to sort of do all the checking and implementation ourselves in code. So I mentioned output format. And so our main output format is we actually have a binary format that is encoded that's based on Postgres's binary format and gets decoded by our clients. So objects get returned as native Postgres types. The object shapes are returned as records, and as rows is the record type in Postgres. And then things that have properties and links that have possibly multiple elements because they're multi get turned into arrays with ArrayAg. And the client is sent a type descriptor that we can compute in advance that describes the format that they use to drive the decoding. We also have a direct JSON output mode where the SQL query produces JSON directly. All right, and so what does this end up looking like? All right, so here we've got that basic title, release year, actors query. We're filtering Dune, and you can see that we are down at the bottom selecting from a title named movie. And for some reason, cross-joining with the computation for whether the movie matches a parameter. And, that's just because we're not writing code that humans need to read, and it's easier to generate that way. But if you're actually writing the code, you do it differently. And then up at the top, we are selecting the ID, the title of the release year, and then in a big nested query, we are doing an ArrayAg of a subquery where we select from the movie actors link table and a person table and collect all of the persons who are acting in the movie. And here, just briefly, I want to talk about my number one complaint with SQL, which is that the clauses are written in the wrong order. So this should be from whatever and then select. And I think, honestly, that would already get you a 50% better SQL, just putting the from before select. Though, obviously, we've gone further than that.
You know why it's from? The select comes before the from, right?
No, I don't. There.
So when IBM first created SQL, they did a user study at Arizona State University, right? And they had from before select. And then they did a user study, and this is like the 70s. And the students complained at Arizona State that it was too confusing, and they wanted the select before the from. That's why it's that.
Fascinating.
Yeah.
Wow.
Okay. That was from Pat Salinger. All right, sorry, keep going.
Yeah, all right. But so we actually I spend a lot of my life looking at SQL query debug output because we send a query in and then we're trying to debug why it's not working, or I'm trying to implement some new features. So I spend a lot of time reading this ugly SQL output. And so I actually have a mode in our pretty printer that puts the from before the select. And so I use that whenever I'm reading our output. We call it SullyQL, or SQL for short. Yeah, so the code we generate is kind of ugly. There's at least one extra query in here, but Postgres doesn't care too much. All right, so what does performance for this look like? I had meant to put in graphs, but wasn't sure where up-to-date graphs were, and then I forgot to remove the to-do graphs from the slide. But we do all right. We are better than the ORMs we compared with. I think we've got some benchmarks on our website. We tend to be a little worse than the best handwritten SQL, but that's the best handwritten SQL that's doing the same sort of ArrayAg tricks that we are, that returns all the nested data in the way we care about. If you're writing more idiomatic stuff, then it's not clear. Then usually we can do better. If you're doing ORM style n+1, or even if you're trying to fetch all the first rung and then the second rung, if you're doing the 2 or 3 query style.
Just be clear, when you say you're better than ORMs, like Hibernate's going to do, or Active Record, they're going to do the N+1.
Yeah.
Uh,
A lot of them do N+1, and we obviously cream them. And then there are some better ones that'll do like 3 queries, and we still do better than that. I don't think there are many yet that that do what we're doing, though obviously they could. So
I'd be also curious. I mean, we talked this at the end. Like Postgres is their query optimizer is terrible for nested queries. Like you have that cross join lateral. I'm assuming you can't decorrelate that or clean that up.
No, it turns this. It does. If we do this, it does the right thing. It'll do a with that outside cross join lateral where that's where the actual like index lookup is. No, it'll generate an index scan from that.
Okay.
Yeah, or else we would have stopped generating code like that, because obviously being able to hit the indexes is. We should maybe still stop generating code like that, because I bet that in more complicated cases we're leaving money on the floor. But all right. But so we still support SQL, right? So it's sort of SQL and death. And originally we didn't want to, because we sort of felt that like if we support SQL, we're just going to treat that as an escape hatch. And so like we wanted to not support SQL partially to force us to make EdgeQL be able to solve all of people's needs. But that turned out to not be realistic. The big thing is like people wanted to be able to attach existing business intelligence tools to it. And that wound up being a really important use case that a lot of users and potential users wanted. So we had to build that. This was a couple years ago mostly. And this was a surprisingly to me big pain in the butt. And the reason for that is a couple things. So one, in our implementation, right, everything, all of our tables and columns have UUIDs for names, and changing that, like that was for a bunch of technical reasons that would be difficult to backtrack on. And we didn't want to compromise too much of the core thing for the SQL support. But we also wanted our inheritance to work naturally in SQL, so that selecting from the base type would select from the children type as well, like it does in core EdgeQL. But we also wanted to expose a clean database to users that only had like nice names, user and movie, and not our UUIDs, which meant we couldn't just create views with nice names. And also we need to, okay, right. So to do that, we had another compiler, because we're compiler people, so we solved it with a compiler that translates names and does some tweaks. It takes in SQL and produces SQL that references our actual internals. But then what turned out being the really hard part was that all these tools want to introspect the schema using information schema and PG catalog. And that was just like totally miserable. Honestly, I think one of my reports almost quit building this. But we basically got it working. The users like it. But only supporting reads is not fully satisfying. There are lots of people who want to be able to do writes, and people who sometimes want to be able to use their existing ORMs to work with EdgeDB or GEL, which is very frustrating, because part of our whole goal is like, ORMs. And then there's also this theory that supporting writes would allow easing migration paths, right? Because you can still come in or come out through SQL. This one was less surprisingly a huge pain. Like I mentioned before, GEL schemas have all sorts of stuff. They've got access policies, triggers, and rewrites, and all of those are implemented in the compiler and not using SQL features directly. Like I said also before, we don't have foreign key constraints. That's enforced by the compiler. And so we needed a way to do SQL writes that were respecting all of the invariants of EdgeQL. And so the solution to that was to use the EdgeQL compiler to generate the proper EdgeQL safe data modification language queries, but arrange to feed them with results from user written SQL. So we've got a query that's like half produced by our SQL to SQL compiler and half produced by our EdgeQL to SQL compiler, and then knitted together. And I'm really happy with how this turns out, but this is one of those things where it really does seem like we made things hard for ourselves, right? Like we've got Postgres right there, and writing to it from SQL seems like it shouldn't be so hard, but when you're trying to sort of build a model on top of it that's its own model and not SQL, you make a lot of hard stuff for yourself. All right, so that's Gel. I ran you through what we're doing, how we're doing it, both with our language design and our implementation, and then how, even despite this being SQL or death, we still wound up with both. All right, thank you. Do we have any questions?
Awesome. So I will clap on behalf of everyone. That's a great talk. Let's open the floor to questions.
Yeah, maybe I can start. Michael, that was a really nice talk. And as we've discussed, as you guys have been discussing through this presentation, SQL has all these ugly limitations in terms of what you can express. And there's obviously a rich history. Your work reminded me a lot of the object-oriented database work that people did, trying to get inheritance and trying to get this type of nested structures in a very easy and a natural way from the application perspective and leave the complications out. The main challenge with all of that work is often related to like what kind of applications are you supporting? And a lot of the object-oriented database systems were very good at supporting complex business logic types of applications that needed that rich relationship. So could you talk a little bit about what kind of end applications and application programmers really like to use GEL?
Yeah, we're mostly targeting sort of traditional like web app development. We've targeted a lot of like the TypeScript community and Python community, people doing just that sort of development. We've had working with our users, we found a lot of people who do have pretty complex object hierarchies and schemas and lots of intricate data models. The ones who seem both most excited and also talk to us the most for support, because the further you push it, the more likely you're to run into problems with new technology.
Got it. Thank you.
Jonathan, go for it.
Hey, Sully, good to see you again.
Yeah.
Question on language design. So links make a lot of sense for this as in your model. But then I got surprised that you had attributes on the links. And,
sure.
and I thought, well, you could just have more objects for those things. So I'm curious
That's true.
to probe that design a little bit and see, why you chose to do that, and does it cause, complications? Is it mostly kind of a usability thing, or are there technical reasons for it?
Yeah, and so it's mostly a usability thing. It's the idea is that you sort of want them to be there on the object for, like you want to be able to add the links and then set the link properties at the same time. And you want to be able to drop the link by like updating the object and dropping all the links, and then all those intermediate rows get deleted. Whereas if you put it into a separate object, now you've got the separate relation, and if you want to remove it, you've got to go be deleting this other object. That said, like link properties are a tricky part of the model and cause us more implementation woe than like almost anything else. And have probably more bugs in them than any other part of the query language. So there are sort of user benefits, like expressiveness benefits to having them be built in, but you can mostly replicate them without using them. And it'll be sort of less elegant, but easier in other ways.
Got it. Thanks.
I mean, I want to say attributes are they're standard in like the graph databases.
Yeah.
So it makes sense.
It's like
okay. Yeah. I don't have the graph database background, so
you're not missing anything. Don't worry. All right. So Nick in the chat asks, can you talk more about inheritance versus composition in the schema? I think you said inheritance was best used for mixins, which in object-oriented don't use inheritance. The purpose is to avoid it. I think you also mentioned some pain associated. Do you mind sharing the issues?
Yeah, so one of the one thing is I don't just mean mix-ins from like a language perspective when languages have specific mix-in support. There are lots of object-oriented languages where you do use inheritance for mix-in style stuff. It's like common in Python, and that's where some of the DNA for our language comes from. We tend to support we support inheritance and then we support composition via links, but not via anything that sort of internalizes it into the object itself. EdgeQL is built on top of Postgres. Should I just move to the next question, or do you want to?
Yeah, no, go for it. Go for it. Just read the question.
So the question is, since we're built on Postgres, can we be used for Postgres spatial queries? And the answer is, EdgeQL is built on Postgres, but it can't just automatically use any Postgres library, right? We need to make sure to it needs to have a wrapper that works with EdgeQL in order for it to fit, because not everything fits our model. And we don't want to let users call arbitrary SQL functions because it can sort of break out of the model, especially in our cloud and stuff. But that said, with 6.0, we released a PostGIS plugin. So we now support PostGIS.
Nice. All right, Jonathan again.
So I was not surprised that you need to support writes, but I was a little surprised that it came in the part of your talk that I thought was, oh, here's the kind of optional things that we found we needed to add to to support users. But like, how do you get anything in the database if you can't write?
No, sorry, that's only from SQL. Only supporting writes from the SQL side. EdgeQL already has its own stuff for writes, inserts and updates and deletes that I mostly skipped over because
okay. So this is you have a coherent model for doing this in EdgeQL.
Yeah, we have a good model
SQL
for doing
compatibility.
EdgeQL. Yeah, it was just the SQL writes that. Well, actually, EdgeQL writes are also hard in a bunch of ways, but yeah. There's also the question of what are some of the pain associated with object-oriented? And a lot of it is in our schema modification. Like if you add a property to a parent type, you need to propagate it to all the children and things like that winds up being a big pain. And then also in query generation, doing things like enforcing exclusive constraints between related objects get kind of painful. And I probably don't have time to talk about this, but get painful in a way that's actually weirdly related to my PhD thesis on weak memory.
Another question from Prakash.
So I had a question on the implementation side. So looks like you probably don't need to put any constraints on the tables that you defined. For example, the links table had unique constraints on both the source and the destination.
Yeah.
So you could have gotten away without putting in that constraint, right? And enforcing it in the compiler?
Yeah, probably.
So do you put those constraints because you're looking for something that Postgres should do with those constraints, or?
Well, even if we didn't have a unique constraint, we would want an index. And since we're putting an index and it is unique, we put a unique constraint in the hopes that that will guide Postgres's optimization in the right way.
So another question. So in the GEL language, if I wanted to do an arbitrary join, like a movie name equal same as an actor name, so that's not possible, right? Is that our joins only traverse?
Here we go. Can everyone see the bonus slide?
Yes.
Yeah, here we're doing a join to get any actors in movies that have the same first letter. Apparently, Anthony Mackie was in Ant-Man. I don't remember that.
Mm-hmm.
I didn't remember that. Falcon showed up.
And one last question. So how Like if you were to compare this with property graphs like Neo4j or one of the other ones, right? Is this very different from those, or?
The implementation is very different. The query language is very different. It's strongly typed in a way that those tend not to be.
Mhm.
The operations and the targets are pretty different.
Okay. Okay, thanks.
But you could also definitely, I think, map our model to a graph model, right? But I feel like you'd probably lose a little bit of fidelity doing it.
All right, next question is from Eric.
All right. So my first question is, I saw you support a count. Do you support anything like a group by statement?
Yeah, we've got a group by statement.
Were there any complications for how the schema understands it?
I don't think there were any complications for how the schema understood our group by. There are a lot of implementation complications in it, partially because we try to provide a much higher level group by operation than SQL does, where you can do like arbitrary operations on the groups, and then if they can be compiled directly into SQL aggregates, we do, and otherwise we sort of aggregate them manually and then process that.
Right, makes sense. Okay, last question then, a bit of a strange one. For me to say, this does remind me a little bit of the OData data model. I don't know if I was wondering if you're at all familiar with that.
I'm personally not.
Which data model?
OData.
Spell it.
ODATA.
ODATA.
It's more of an enterprise type thing.
Yeah. I don't know how to call that a data model. It's more like a specification, right?
Yeah, but especially I'm thinking about the fact that OData doesn't do joins. They have an kind of idea of the properties that are linked to other properties that are either like or single values. So that seems a little familiar to this model here.
Actually, this goes. I think this is most similar to the semantic data model. We have sort of linking between the entities. That goes back to like 81, 82, 83. There was some earlier work done on that. But I don't think anybody built the real system. All right, cool. So I'll finish up with a few more questions. So since you have this approximate cardinality, the sort of the many, at least one, like I wonder if you guys could use that to pass Postgres, like query plan hints about, I don't know, actually, I don't know if Postgres would support this, but like to say, this is going to be, reading one record. If it's unique, then if it's a unique filter, then it'll know that. But for other things, you may know. Like, if you guys pass any hints, you just throw SQL at Postgres and let it do whatever it wants.
Right now, we just throw SQL at Postgres and hope it figures it out.
Okay.
A bunch of times you'll wind up with, Sometimes you wind up with things in subqueries, like subquery expressions, and then it should know that if it's not one, then it's going to be a error. But
so, I mean, in our research, we found like the Postgres optimizer is one of the worst ones compared to like Oracle, SQL Server, and others to do like unnesting of subqueries. Have you guys tried just as on a lark pointing gel at like DuckDB, which speaks the Postgres SQL dialect, but it has a better query optimizer, just to see like, are there examples where DuckDB can generate better query plans than what Postgres can do, to give you an idea of like what you're leaving on the table?
We haven't tried pointing it at anything else. Does DuckDB speak Postgres?
Yes.
Like at what degree of fidelity?
The Postgres, it's not gonna do the wire protocol, but it'll do SQL. Like they use the Postgres parser, SQL parser.
And they support all the same function. Yeah, maybe. We are pretty deep on Postgres.
Of course, yes.
And so haven't thought in a while about pointing it at other things.
It's just like when I start seeing the subqueries, I'm like, oh man, Postgres is going to choke on something. And of course, as you mentioned, some of the customers have very sort of deep hierarchies or inheritance, which would cause a lot of subqueries. And I just wonder how often does Postgres choke?
Sometimes we've had pretty good results, but also sometimes bad results that we need to track down. That's
Sure. And then the last one is, I mean, you sort of mentioned this about migration paths, but like, if I have an existing application, I'm like, gel is amazing. I want to switch to this.
Yeah, it's
I
gonna
have
be
it.
hard.
Okay. Okay. Do you guys like automated tools to help with this, or like someone literally has to go like, rewrite the schema, and then there's like you have to manually import everything in.
We've built some tools, and I can't remember if we shipped them. I think we were like medium satisfied with what we've built. And might push forward with it, but it's like we'll say one of the things is like prioritizing at a small company. It's like, what's the top priority thing to get us traction? And it's like,
Yep. This is clearly for greenfield applications. I was just curious if like, a big company says, "Oh, we're gonna build this new thing in gel. It's so great, but we have all this other legacy crap we want to get on gel too." And you're like,
yeah, our targets have mostly been people building new stuff.
Yep.
Because that's just the easiest customer for any new database, right? Because
yes,
data migrations are going to be painful even if we have really good tools, and we have medium tools. So